So last time we introduced the dimensional analysis to actually study scaling dimensions of various terms and parameters in Landau theory or the five-fold theory. And today we will apply this dimensional analysis to get some of the critical exponents predicted from the Landau theory that we already learned. But in fact, we'll show that this kind of a dimensional analysis plus the only length scale, which is a correlation length, which diverges at a critical temperature, and that kind of concept is not sufficient, because we'll see in just a moment that from dimensional analysis, at least for these two behaviors of the correlation function g and also the correlation length itself, is not sufficient to capture anomalous exponent associated with this correlation length exponent and also the exponent of the correlation function g. So in other words, from the simple dimensional analysis, we will get the incorrect critical exponents for the correlation function g and for the correlation length c. So we will demonstrate this kind of simple dimensional analysis, and later we'll point out what the problem will be. Okay, so first let's remind ourselves the definition of the correlation function g between these two spatial locations r and r prime. So this is the phi-phi correlator, where phi is the order parameter in the Landau theory. And from the standard statistical mechanics, we know that this is given by this kind of a ratio in the denominator. This is simply just a partition function in the kind of a coarse-grained Landau theory. And this effective Hamiltonian is the Landau's free energy functional. And in the numerator, you multiply this Boltzmann weight again, then you should multiply this phi of r and phi of r prime. Okay, so this follows standard definition of a two-point correlation function after ensemble average. And we know from previous lectures that the dimension of this phi goes like 2 minus d divided by 2. So this g of r, since it contains just two order parameter multiplied together, therefore it has the dimension of phi squared. But other prefactors or other factors, such as this exponential factor, are all dimensionless, as we discussed last time. Especially the H effective, written in terms of the dimensionless variables, the coupling constants, which we defined last time. So then you plug in this dimension of phi to this dimension of a Green's function or correlation function, you get this is L to the power of 2 minus d, which leads to 2 minus d as the spatial dimension for this g of r. And you could Fourier transform this Green's function to k space, and again you can count the scaling dimension of g of k by this Fourier transform integral, and you simply just make a product of all these different powers in length scale. For example, this v stands for the volume, which goes L to the d, but this is in the denominator, and this integrand is actually dx to the power of d and dy to the power of d, and so on. And this exponential factor is dimensionless, and this gx minus y goes as L to the power of 2 minus d, shown there. So you simply just put everything together, and you get this L square dependence. And so you conclude that the dimension of g of k goes as L squared. But there's one important relation between the length scale and momentum variable k, is that k is actually proportional to 1 over L, or vice versa. Remember, momentum or wave number, the Fourier variables k is actually inversely proportional to the length scale from your quantum mechanics. You know that. So in other words, we could translate this kind of a dimensional analysis back to the real space or Fourier space. You could go back and forth. We take this dimensional analysis from the start, and we take advantage of this inversely proportional relation between k and L, and we know that g of k in k space has a dimension k to the power of minus 2, because L is inversely proportional to k. And likewise, g as function of L has a spatial dimension, the L to the power of minus 2. So now you could rescale your length scale. Say L prime goes like B times L, and or K prime goes like K times B. Then G prime as function of K prime goes like B to the power of minus 2 times G of K. Okay, so you could simply read out this result by simply plugging this dimension of G of K in K space, and you see that when you transform this K to K prime by a factor of B, then this G prime, this function of K prime, will have a factor of B to the minus 2 power in front of G of K. So now, if you look at this Green's function in K space that we obtained earlier, which is in this kind of a Gaussian form of the Landau theory, and then this is given by 1 over R0 prime plus K prime square, right? R0 prime is proportional to T minus Tc, and which is the distance to the critical temperature. So now let's look at the dimensional analysis for this R0. And as I mentioned, this R0 has a spatial dimension of L to the minus 2 from our previous study. And this is equivalent to the K to the power of square, K squared. So if I transform this K prime by a factor of B relative to this K, then this R0 prime transform like B squared times R0. So that simply comes from the fact that R0 has a spatial dimension of K squared in K space. So then you simply just plug in the relation between prime and unprime variables by including the factor of B or B squared in this G prime form, and you get this 1 over B squared R0 plus B squared K squared. So then you simply just take out this B squared from the denominator, and you get B to the power of minus 2 times G of K. And this is precisely what it says here. So this relation coming from the dimensional analysis of R0 and K of our previous obtained Green's function, the K space, actually is identical to the simple relation that comes from this dimensional analysis of a Green's function itself. So either way, you get the same conclusion that G of K behaves as B minus 2 power times G of K, or G of K prime. Good. So coming back to this previous obtained form at T equals Tc, which means that R0 vanishes, then this G of K is simply behaves as 1 over K squared. Okay, because that term goes away. However, as we pointed out some time ago, that the real Green's function corresponding to the correct or rigorous solutions of this IC model, some sort of related models, oftentimes it carries extra exponent called anomalous exponent eta apart from this 1 over K squared dependence. So there's 1 over K to the power of 2 minus eta, where eta is non-zero. But here, by simple dimension analysis, we only conclude that this eta is 0. But in reality, for example, in two-dimensional Ising model, this eta is given by a quarter, 1 over 4. Okay, so it's not 0. And similarly, this kind of a scale transformed, the Green's function under this length scale changes behaves as b to the power of minus 2 plus eta. So it is not this b to the power of minus 2 shown over there, but there is an extra anomalous exponent called eta appearing here in the real, say, or more rigorous solutions of this Green's function at the transition temperature. So that is the first example to show that the simple dimensional analysis is not sufficient to capture the more realistic exponent of a Green's function. So let us just take a second example, the correlation length. So our Landau theory or mean field theory, or Gaussian theory, tells us that this is proportional to R0 to the power of minus 1/2, which is proportional to little t to the power of minus 1/2, where little t proportional to t minus tc divided by tc, right? But in reality, this nu, which is the exponent appearing in front of the inversely proportional to t to some power, this is called the correlation length exponent, is not 1/2. Okay, it is slightly different from 1/2. Okay, of course, it's not a big difference, but this difference is actually sizable. You cannot ignore that difference. So based on this analysis, we conclude that it is not sufficient by using simply just dimensional analysis plus this single length scale involving in this phase transition, which is the correlation length, played as a single length scale. No. So there is another length scale involving at a transition in addition to this correlation length. Of course, correlation length divergence is important, but there's another length scale we call the microscopic cutoff or the lattice spacing. Little a will get involved as well. Okay, so after the break, we will just illustrate or demonstrate how this microscopic cutoff will get involved to modify this simple naive predictions by a Gaussian theory of the Landau's free energy functional or simple dimensional analysis that we just did over there. Okay, good. So let's take a short break. Okay, so we continue. As I mentioned, this correlation length C may not be the only length scale that is important at the transition. There is another important length scale, which is the microscopic cutoff or the lattice spacing A, involving in this so-called scaling function near the transition. So let us just re-examine the correlation function g of k at the transition. As I mentioned, this g of k at Tc goes like 1 over k squared. But you could think of this 1 over k squared form as just one factor. There should be another factor, an unknown function, f function, which is a function of a dimensionless variable a times k, where a is so-called microscopic length scale, little a, lattice spacing, and k is the momentum variable. So a times k has no dimensions. Remember, a and k are inversely proportional to each other. So this function f near or at the Tc behaves as some variables which is dimensionless, a times k. So this is a function of ak. All right, so it involves both this microscopic length scale a and also the momentum variable k, and in the special form of a times k. Okay, because this can only be a dimensionless function at the transition. But in general, this function, f function, may not be a finite constant valued as little a approaches 0 at a transition, or a times k goes 0 limit. This f function, the function of a times k, it may not be just a finite constant. Suppose this behaves as a power law vanishing function, and this is proportional to a times k, the product of a times k to the power of eta, and eta is exactly this kind of anomalous exponent that we just mentioned a few minutes ago. So in that case, if you plug in this special power law behavior of a times k with a power law exponent eta, then you could easily see that this Green's function in Fourier space at the transition temperature Dc behaves as little a to the power of eta divided by k to the power of 2 minus eta, where you know very well that this is precisely the correct power law behavior at a transition in the realistic spin model that we just mentioned. In two-dimensional IC model, eta is equal to a quarter. So of course, this Green's function, this kind of a revised version of Green's function, carry another power law in microscopic length scale a, but you could check that this is precisely what we need when you do the rescaling for the momentum variables, goes from k to k prime, where k prime is b times k. So let's just check this. So a times k is the same as a prime times k prime, because a times k is a dimensionless quantity. So if you rescale your momentum by a factor of epsilon, then A prime, the length scale, should behave in the opposite way, which carried 1 over epsilon factor in the scale transformation. And as a result, you can easily see that this G prime, K prime at Tc to carry this factor b to the power minus 2 or epsilon square inverse over there, where epsilon is precisely this factor b here. So you see, this little a to the power of eta actually saved our argument to actually preserve this kind of scale transformation of a correlation function while it maintained this anomalous exponent eta appearing in this correlation function in K space at Tc. So you see these two results are simultaneously satisfied. So that's the trick. And it's not a trick, it's not a mathematical trick. I think we have reason to believe that this is exactly what happened, that this microscopic length scale play a role near the transition or at the transition to actually give rise to anomalous critical exponents apart from this kind of simple naive Landau's mean field theory or Gaussian approximation. Okay, so with the help of non-trivial power law in this f function, and that we could simultaneously get this scale transformation that we obtained earlier, while there's a extra exponent eta in this Green's function as functions of K space variable at the transition. So these two actually results are satisfied at the same time, which is highly non-trivial. So it is not sufficient to actually have just a single correlation length involving at the transition. So it needs two, okay? The correlation length and the lattice spacing A. So we need two variables to actually reproduce the correct power law exponents that we measured in the experiments. Otherwise, you always end up with the Gaussian critical exponents which deviate from the observed exponents in experiments, or a more exact, rigorous theoretical results. So this is just a first re-examination of this correlation function. Let's re-examine another one, which is correlation length exponent nu, which, remember, this is the exponent appearing in the near the transition as function of little t to the divergent power minus nu. So you could actually do the power counting of this correlation length and little a and r0 as we did. So again, you assume that there's another microscopic cutoff little a involving in a divergence of a correlation length, which is the f function that we just assume over there. And this, again, the f function is a function of r0 times a squared, because r0 carries scaling dimension of minus 2, L to the power of minus 2. And this argument inside this f function should be a dimensionless quantity, which should behave as a combination of a squared times r0, which we call this x. So again, f function is function that x may behave in a highly non-trivial way, and we assume that it has this non-trivial power law exponent, x to the power of theta, near the transition. So you plug in this extra power law, x to the power of theta, and you get the modification or correction of the correlation length exponent nu, or nu revised, which is slightly different from this 1/2 of a mean field prediction by minus theta. So theta is a small number, smaller than 1/2, which will make this nu equals to have shifted slightly away from 1/2. And that is precisely what the observation tells us. 1/2 is not, the accurate exponent in many experiments of, say, the Ising model. So you could actually go back to the table that I showed you some time ago regarding the prediction from the Gaussian theory or Landau's mean field theory, and the exact calculation and experimental results. So there's a big table in a textbook that you can check, and when you check this table of this critical exponents, you will see clearly that the nu is not precisely 1/2, but slightly away from 1/2. And that deviation is precisely theta that we define here. So the lesson we learned here is that in general, near the critical point the thermodynamic function or any observables as function of correlation length and also this microscopic cutoff lattice spacing. So it depends on both A and C, and in the special combination, which is C to the power of some exponent nu times the f function, and this f function is a function of a dimensionless quantity. So if both little a and c have the dimension of length scale, then this function f should behave as a divided by c or c divided by a. Okay, so that combination is a dimensionless variable. Again, as this little a divided by c goes to 0 near the transition where this correlation is diverges and this lattice spacing goes to 0 limit, then there are two possibilities of this f function should behave. The first possibility is that this f function is simply just a constant, which is precisely what this mean field theory assumed or the Gaussian theory assumed. But there's a second possibility that is precisely what we assume over there, that the f function behaves in a highly non-trivial way. It carries some kind of anomalous power law involving, in addition to some scaling function phi, which is a regular function. This is a regular function. So the value of this extra critical exponent or extra anomalous exponent sigma in general does not depend on the microscopic cutoff A. So this sigma has nothing to do with this microscopic length scale. But we need to assume the dependence of this scaling function, this microscopic lattice spacing. However, the critical exponent do not depend on little a. So this is sort of a correction to a general concept that we mentioned in the very beginning of the course, that near the transition, the correlation length diverges. And the correlation length is the only length scale that involves near the transition. The answer is no. This statement is not accurate because of precisely the extra exponent, anomalous exponent involving in a real system, which is also a possibility here. So that concludes our chapter 7. And after the short break, we will start a new chapter, which is the scaling and scaling laws and scaling hypothesis that we introduced in the very beginning of the course. But here we should more rigorously derive, based on this scaling hypothesis, all this sort of various critical exponents and their relationships called the scaling laws, and which is the foundation of all these critical phenomena, the scaling laws. Okay, so let's take a short break. Let's continue. So we now start a new chapter, which is about the scaling laws or scaling hypothesis or scaling relations, which we introduced phenomenologically in the very beginning of our course in September. Back then we simply study this phenomenology of the scaling from experimental point of view. But now, since we know all this definition of critical exponents and Landau theory, we should be able to understand why there's a scaling relation or this scaling properties from the theoretical point of view. So let's just summarize all these critical exponents that we have introduced so far. The first two sets of a scaling function is the correlation function, g of r and g of k, which we just introduced a few minutes ago, where there is an extra anomalous exponent eta appearing in these two correlation functions near the transition, which behaves in the power law fashions as function of this real space vector r or this momentum space variable k. But there are other various critical exponents that we already introduced many times in the past. For example, this magnetization near this transition temperature behaves as little t to the power of beta, and at the transition temperature dc, this magnetization behaves as external field to the power of 1 over delta, and the specific heat goes like t to the minus alpha in the power law fashion, where alpha is called the specific heat exponent, and isothermal spin susceptibility chi behaves as t to the minus gamma. Right? Remember, gamma is 1 for the Ising model. and the correlation length exponent nu near the transition behaves as t to the minus nu. So all this alpha, beta, gamma, delta, and nu are called critical exponents, and they could be either calculated or measured in experiments. But this is not what this chapter is about. The chapter is about these exponents are not independent variables. They are related to each other by so-called scaling laws. And the scaling laws can be either derived from kind of a scaling hypothesis that Whedon proposed, or they could be checked by the experimental data. Of course, this from the experimental is having always some kind of error bar. But analytically, one could derive such a relationship based on this Wheaton's hypothesis. But what is the scaling law, or what are they? So there are three important scaling laws. Oftentimes we talk about the scaling behavior or critical exponents. Number one is called Rushbrook's scaling law, which involves the linear combination of alpha, beta, and gamma, where alpha plus 2 beta plus gamma equals 2. So we will derive such a relation in the coming time. The second relation is about this beta times delta equals beta plus gamma. So it looks kind of complicated, but they all come naturally from this scaling hypothesis or scaling behavior of free energy, or scaling ansatz of free energy. And that free energy is basically the Landau's free energy. And the third scaling relation is called Josephson's scaling law, which involves 2 minus alpha equals nu times d. And this is the only equation that involves the spatial dimensions, d here. The relation number 1 and number 2 do not involve spatial dimension d. But the third relation is Josephson's scaling law involves scaling this spatial dimensionality d. Oftentimes we call this hyperscaling relation, which is the relation among this critical exponents, which also involves this dimensionality d. Okay, so we will derive the three scaling laws in the following content. Okay, so there's a side remark that the first Rushbrook's scaling relation comes from the thermodynamics requirement that alpha plus 2 beta plus gamma should be larger than or equal to 2, but this equality here, but these thermodynamics requirements actually inequality, but this inequality near this transition will become equality. Okay, so this relation holds in general. Okay, so this is just by thermodynamic stability consideration that this is the case. So you could check how you derive this inequality in the textbook or in other references. We may not have time to discuss that, but at the transition, this inequality becomes equality, which we call Rushbrook's scaling law. So now, how to understand or derive the relationships among all these different exponents? Edward Whedon, who is the theoretical physicist in Princeton University, and he proposed a very clever way to actually combine all the information we have regarding the magnetization of a kind of an Ising-like model near the transition, both at a small deviation from the Tc in the temperature domain, as well as a little external field h near zero field limit. So both little t and little h are very, very small and close to zero. In that limit, there are two different behaviors of the magnetization. The first is when you quench this external field, little h vanishes, and you just look at this behavior of the magnetization function little t. And as we mentioned that for example, the Ising model, when little t is positive, you are above the transition temperature, and the magnetization, of course, is zero. But if you are slightly below the transition temperature, then this behaves as t to the minus power of beta, right? So that's what we already defined. But it depends on the sign of this little field, which may take positive, negative value of this magnetization. On the other hand, if we are fixed at the transition temperature or little t vanishes, then we look at this magnetization function of the h, and we know that this m behaves the magnitude of the h to the power of 1 over delta, which we defined over there, and with some kind of prefactor, and also plus minus sign, depending on which side of this external field that you are talking about. So in fact, these are three different phenomena, okay? Zero field above or below Tc, or at the Tc but at finite field. So these three behaviors can be combined into the single scaling form following the Witten's proposal that we already introduced in the very beginning of our course, that Witten cleverly, very smart way of defining this magnetization as functions of both little t and little h near this transition by defining so-called scaling functions or scaling forms, capital F plus minus, plus for temperature above Tc and minus for temperature below Tc. So you can see that these two forms are almost identical, very, very similar in a functional form, except now you just put the plus and minus to actually represents the scaling functions above and below the transition temperature. And other than that, this behaves t to the beta and t minus t to the beta is the same, and this f plus and f minus are both scaling functions of the h divided by t to the power of delta, and delta will be determined later. So of course, for different fields and temperature, this magnetization as a function of temperature for fixed fields or as a function of the field at a fixed temperature, they all curves which are well separated. So they're all independent curves. They look independent, but they are not independent, because if I follow the Witten's proposal and make a special plot of this x and y axis, and the x-axis actually the argument inside this f function, the scaling function, capital F, which is magnitude of the field divided by magnitude of the little t to the power of delta. If I plot those independent curves against this x variable and also against the y variables, which is the magnetization, magnitude of magnetization divided by magnitude of the little t to the power of beta, if I intentionally reorganize my data sets, and I could merge all the data into two scaling functions, capital F plus and capital F minus, which are precisely defined here. So that's a very clever design of a unified scaling form of a magnetization near the transition. And you can see this kind of two sides of the transition, the scaling form show the same general feature, except now this f plus and f minus functions are two different functions, but in this functional form above and below the transition, they all look like the same, okay? Which means that above Tc and below Tc, I could consider magnetization behaves in a similar or exactly the same way. Of course, the f plus and f minus function are two different functions, but this functional form are identical, okay? So if I follow Witten's hypothesis, then I could use the thermodynamic relations. Actually, we can take the derivatives m respect to the field, get susceptibility, and so on and so forth, and we could relate all these exponents, beta, delta, alpha, gamma, and nu. So these relations are all derivable from the Witten's scaling hypothesis. So this is a very important hypothesis in the field of phase transition. So let's look at the behavior of this f function. So first, there's a time reversal symmetry involving here, as we mentioned that this magnetization changes signs if you change the field, the sign of the field from plus h to minus h. So then this immediately tells us that this f function plus or minus f function are odd functions in x. So, and second, when the field approaches 0 and its magnetization behaves minus t to the power of beta, times f minus function, but the magnetization vanishes when little t is positive above the transition temperatures. So that immediately tells us the special values of f plus and minus are different. In the first, this f minus is actually the constant because this is non-zero value. But the second is t positive case, the magnetization vanishes, and therefore f positive when x is 0 is actually 0. But of course, if you just sketch all these curves following the same collapse data, then you could numerically fit f plus or f minus function to some power law or some non-trivial function in x. So let's take a short break. When we come back, we will just start from this Wheaton's scaling hypothesis and try to derive some scaling laws that we just summarized over there. So we just introduced Wheaton's scaling hypothesis to actually combine the scaling behaviors or power law behaviors of magnetization of an icing system above and below the transition temperature, and it holds for both above and below the transition temperature in the single scaling form, except that now this f plus and f minus functions are different, but the functional form look exactly the same. So now we take this Wheaton's scaling hypothesis as a starting point for magnetization near the transition temperature and the zero field limit, and we could calculate all these critical exponents from these thermodynamic relations. So the first quantity we could do is to calculate zero field susceptibility, which is the partial m partial h. The capital H refers to the external field, and the little h is the dimensionless field, which is capital H divided by kBt that we defined already. So we can follow the standard relation between the susceptibility and the magnetization, that if you take this first derivative of magnetization is back to the little h divided by kBt, you get susceptibility in the zero field limit. And you plug in this scaling hypothesis that Wheaton proposed as a general form, both below and above this transition temperature. So you just to take this general f function plus or minus depending on which side of the transition that you start with. And if I take this capital F, the x, where x is just this quantity h divided by t to the power of delta, then you could get to this form. The t magnitude to the power of beta minus delta times this first derivative of the f function with respect to the x evaluated at x equals 0. So now let's further assume that this prime function, this derivative of this capital F for both plus and minus side of the transition, evaluated as x equals 0, actually well behaves, meaning it's not 0 or infinity, it's just some finite value. Then we can simply just consider this just some kind of prefactor, constant prefactor, and we could simply just compare this definition of susceptibility near the transition as t to the power of minus gamma. Remember that. That's a definition of a gamma exponent. So, but now the gamma should be equal to what? Delta minus beta, because these two power in t should be identical. So then we get this relation here. This is not a scaling relation, but it tells us that this delta that we assume to be in the x variable in the denominator here is not a new exponent. Okay, it is nothing but beta plus gamma, and both beta and gamma are known critical exponents. So this capital delta is just a sum of this beta and gamma exponents, nothing new. So that's again the very powerful hypothesis, because even though we don't know what this delta is when we didn't propose this scaling hypothesis, but we could calculate and compare the known result or known power law behavior of the susceptibility and know that this delta is nothing but beta plus gamma. So now we can take this information for granted and for later purposes. So now let's look at another scaling law, which is the scaling relations. And we start from this limit when this little t goes 0, but the field is finite, small but finite. In that limit, you could find that this f function approaches to f plus minus infinity, where this argument here approaches infinity when the field is small and also the little t is small. And little t goes to 0 limit, but little h remains finite but small. In that limit, this denominator almost vanishes, so then this whole argument x becomes infinity. So in that limit, we could actually compare all these different forms of magnetization and find out what this delta in relation to beta and gamma and so on. So again, we know that this is the standard definition of the magnetization at the transition temperature, but at the finite field, which behaves as h to the power 1 over delta, and we further assume that this f function, f plus minus as function of x, in the limit of x goes to infinity, behaves as x to some power, which we call the lambda. Okay, and that's another powerful prediction or assumption based on this Wheaton's hypothesis that this f function is a non-trivial power in x in certain limits when x goes to 0 or x goes to infinity. So this f function is something like what we introduced earlier for this correlation length exponent or this correlation function. This f function may not be a trivial constant. It may carry non-trivial power in the argument, as function of the argument, and that power is assumed to be x to the power of lambda. If this is the case, then I don't know what lambda is, but I can calculate and compare different forms, power law behaves as magnetization, and then we could find out what this lambda is. So then you could simply just take this lambda, x to the power of lambda, and plug in to this scaling form from the Wheaton's hypothesis. And then we could find out the resulting power law behavior as function of little t and little h, which behaves as little t to the power of beta minus delta lambda times little h to the power of lambda. But let's look at this little t dependence of this magnetization. When little t goes 0, which means that as you approach to the critical temperature, little t goes 0, if this beta minus lambda times delta could be either the positive value or negative value or 0. Okay, there are only 3 possibilities because all of these 3 variables are simply just numerical values. So you could consider when beta minus delta lambda is positive, in that case, when this exponent is positive, then when little t goes 0, this is t to the power of positive exponent, which vanishes as t goes 0. So which means that this magnetization vanishes as little t goes 0, which is not acceptable because we know that this is non-zero value. On the other hand, if this combination beta minus delta times lambda is a negative value, then as little t goes 0, this appears in the denominator in the power law, and therefore as little t goes 0, this diverges. This becomes infinity. So this capital M is either 0 or infinity as you approach the transition temperature, but neither case is acceptable because magnetization is a finite constant. It is neither 0 nor infinity. At the small fields, exactly at the transition temperature, magnetization is a small and finite value. So we cannot, we should rule out these 2 possibilities, and the only possibility we have is they exactly cancel. So beta canceled by delta lambda in this exponent of there, so that there's no little t dependence anymore. So that's guaranteed that magnetization should be a small finite value at the transition temperature because there's no other temperature dependence there to make it either 0 or infinity. So we immediately derive such a conclusion that the beta is given by delta times lambda. But let's look at the h dependence of magnetization when little t goes 0. So now this t dependence is gone. So we can simply compare the standard definition of this magnetization at a small field, but exactly at Tc, which behaves h to the power of 1 over delta, and you compare this two-power law, they should agree, and therefore you get this unknown exponent, which is nothing but 1 over delta, which is again a known critical exponent, and therefore this capital F plus minus as function of the x, when x goes to infinity, behaves as x to the power of 1 over delta. So now you can combine this relation beta is the same as delta times lambda, and lambda is 1 over delta, and you immediately get this relation that beta times delta is the same as beta plus gamma, because we know that delta is nothing but beta plus gamma. So now you use that result, and you can simply combine these two relations, you get this. And this is nothing but one of the scaling laws that we introduced in the very beginning. So this is the magic. It's not a bad magic, but it's a clever hypothesis proposed by Witten, which combined the critical behaviors above and below the transition temperature in a small but finite field. And then we could use the thermodynamic relations and standard definition of the critical exponents and to relate those different exponents together. So they are no longer independent exponents anymore, so they are related. And the relations are called the scaling laws or the scaling relations. So now the mystery is partially solved. So we understand why this phenomenology comes about in the very beginning of our lecture, but now we understand theoretically how they are related to each other based on this hypothesis proposed by Witten, also by this kind of a standard definition of the magnetization, susceptibility, specific heat, and so on from the statistical mechanics point of view. So I guess that's enough for today, and we will continue introducing all the scaling relations based on Witten's proposal next Monday. Again, so next Thursday we have 2-hour lectures to compensate this missing 2-hour lectures on Monday. I'll see you on next Monday then.